Good afternoon. Welcome to Material Witness, in which we're going to take a deeper look at some of the APIs and capabilities of material design and how we use them to implement a couple of demos. In particular, we'll take a look at animations and some of the new color stuff and theming, sort of look at how you might use this in the real world, or at least the real world of the demos that we happen to write. Let's see, which one am I? I'll play the guy on the top. I am Chet Haase. I'm the lead of the Android UI Toolkit team, which is the team that implements all the view widgets down through the graphic stack and hardware acceleration performance to put all the pixels on the screen.
And I'm Romagui, and I work on robots.
And that's all we know about that. So first, let's take a look at a couple of demos. I wrote a very simple demo, and then Romain unfortunately came along and wrote a much prettier one. I prefer mine because I wrote it. Otherwise. So there's a few aspects of this that I want to call out that we'll take a look at in code and capabilities as we go through the talk. One is the activity transition sort of pops out at you. You click on one of these elements, all the other elements fade out, they crossfade into the background because these are not shared elements. In the meantime, we've launched an activity transition, and so we're sharing an element to the next activity, and then that scales up into view where it's been laid out in the new activity. And then as we go into that next activity, how can I play that again? Let's do this. As we go into the next activity, you'll see the little eye icon there. This is a very simplistic animated VectorDrawable that I enabled, and then there's a circular reveal effect to sort of paint the background behind the text that we're displaying there. So we'll see how some of this stuff works.
And this is a very similar demo. You can see here we're using the new palette API to colorize the second activity based on the image that's being loaded. So we're going to look at the last image. And there's a bunch of other effects going on. There's an activity transition with a hero. We just saw a ripple drawable. That's a circular reveal. This is a live map view behind. They can also move in 3D. And this is just an extra little graphical effect that we'll take a look at if we have time at the end of the talk.
So first of all, let's talk about cards. The card view is a new API that we put into the support library, so you can use this on Lollipop. You can also use it on previous releases. In Lollipop, it uses the capabilities that we built into the rendering engine to get real-time shadows. On previous releases, it bakes in those shadows. You get something that looks pretty good. It's not as nifty as the implementation on Lollipop, but we did what we could with what was available. It's also clipped on the borders, so we have rounded rectangles for the cards. And then there's that subtle elevation to give it the shadowed look. You would use capabilities like for cards in implementing the card. Actually, the card that I implemented for my demo, I just went ahead and wrote by hand. It's just a frame layout, and then I just shaped the view and gave it some elevation. So I was sort of mimicking what's going on in the card view API in the support library, partly because card views, I think, hadn't come online by that time, but also because it shows some of the simple capabilities that we have for shaping and shadowing views. So here, there's actually a couple of different ways to implement cards with outlines. One of them is to set an outline. If you're in a custom view, you can set an outline on that custom view and then override on size changed, so that when the view changes size, you can resize the outline appropriately. So that's all we're doing here. We're saying giving a new outline and set it to be a round rect with the following dimensions and corner radius. And then set clip to outline tells us to actually shape the view to that outline. So it's actually going to clip to that simple shape, as well as to cast a shadow from that shape.
Yeah. And going through the outline API means that you cannot use an arbitrary shape as your outline. You're limited to rounded rects, so rectangles and circles.
And then for the shadow, you set an elevation to automatically cast a shadow according to whatever shape you've set on the outline. Alternatively, you can use something that was not in the preview API but is in the public release of Lollipop called an outline provider, or a view outline provider. In this case, it's sort of tedious. If you're not in a custom view, it's tedious to find out about size changes and then change the outline on the fly. Outline provider allows you to do that. You set an outline provider, and then your provider will be called whenever that view needs information about the outline. So the size is changed in the view, it knows that it needs a new outline, it's going to call your provider, and you're going to return back the appropriate information. So here, instead of overriding on size changed, we simply implement the get outline method in the view outline provider interface and return back an outline appropriate to the new size. And then we set the outline provider on the view, and then again we set clip to outline to shape the view. Or, as I said before, you could just use card view, a little bit easier. We talked about cards in previous talks today. Very simple. It's just a container that has views in it. The main reason to use card view is that it gives you a consistent look and feel with other applications and system apps that are actually using cards. So everybody has a consistent elevation, a consistent corner radius, consistent padding for the items inside. Otherwise, it's fairly simple frame layout.
And it was possible to implement card view on your own in the previous releases. And you can see here several ways of doing it. So you could use just a PNG background. It works pretty well for rounded rects. It's not going to work for a circle, obviously. You could also use path clipping, but it doesn't give you entirely clipping. And it was only possible on API level 18. It was also pretty expensive for the GPU to do path clipping, so it's not really recommended. And the last one, I wrote a couple articles on that subject. You could simply use textured shapes, but that would require the content of your view to be in a bitmap, which means that your view has to be static or more static than you want. So if you really need to recreate that effect on previous versions of Android, it's possible. Just take a look at those 3 possible implementations, and depending on what you need, you'll find one that might work for you.
So let's talk about ripples. So this is the idea that you want to give the user information not only that state has changed in their views, but why the state changed. So show them the animation of the state change, that this button is now being pressed. Not only that, but where the button was pressed. So you give them feedback about the actual touch point on the view as well. There's ripple capabilities built into a lot of the standard widgets. So when you press on a button, we're going to show you ripple feedback for the button. If you have a custom view, you may want to use a ripple drawable so that you can get the same effect on your view. Also, there are capabilities that you can add to ripples to have different colors. We'll see some of these things in Romain's demo later on. So here's a simple example of this. I don't know if this comes across in the slide, but just sort of showing as I click on this view, you're seeing the touch feedback before we then actually launch into the separate sub-activity. So there's a couple of different ways to instantiate ripples in XML. You can say, here's my ripple drawable, and that is basically a wrapper around other drawables. So the ripple wraps this other drawable, and then provides the capability to then ripple and sort of reveal that other drawable over time. Or from code, you can instantiate a ripple drawable, and then you can set colors on that to sort of change some of the attributes of that ripple. You can also use this easy approach and just say that your view has a selectable item background, and that automatically feeds the ripple behavior into that view so that when someone presses on it, it knows that it's selectable, and that selectable behavior in the material theme will show a ripple.
Just a little video that show so that the last way of creating ripples, if you use the ripple drawable as a foreground on the frame layout, this is the kind of result you get. So it works really well for complex elements. Here, my frame layout has an outline with rounded corners, and the content is clipped to the outline. It contains an image view and a text view, and then there's just this extra ripple as a foreground.
So how they actually work. So what we wanted to do in this talk was not just talk about what the APIs are and how you would use them in your applications, but also some of the internal details of how they actually work, because frankly, that's interesting. So ripple drawable, as I said before, is a wrapper around other drawables. So it wraps and then it reveals the other drawable over time with this ripple effect. And the interesting bit about ripples is they're one of the 2 animation types that happen on the render thread. So the render thread was something we mentioned in the What's New talk this morning, new capability that we added to the rendering engine. Previously, all rendering operations happen on the single UI toolkit thread because anything that happens with views has to be on this single thread. What we did in Lollipop was to abstract away the rendering portion of that, where we're actually talking to the GPU, from the creation of the rendering commands. The creation of those commands still has to happen on the UI toolkit thread because that's where we're modifying views and getting their attributes. But the actual processing of those commands and turning them into OpenGL operations can happen on a separate thread. The whole reason for doing this was not just because multi-threaded programming is fun, everybody knows that, but because what we can now do is have the ability to have animations sort of foisted over the wall atomically to this other thread so that it can execute on them independently of the UI toolkit thread. So a common example is you might press on a button. This would cause an action that would launch a new activity, a sub-activity in your process. Well, all activities in that process are going to share the same UI toolkit thread, which means that as you launch into that sub-activity, it's going to run on create, it's going to do layout for the first time, it's going to do inflation of potentially lots of views, and all of that is happening on the UI toolkit thread. So any operations that are dependent upon the UI toolkit thread in the initial activity are going to stall while we inflate the new activity. We're actually able to keep the ripple animations running because those are actually running completely separately on the render thread. So you press the button, we have a ripple animation running on the render thread, and then that button may launch a sub-activity. The sub-activity causes a stall in the UI toolkit thread, but the ripple animation can continue. So we're trying to get away from some of these disjoint user interaction points where just because we have this single-threaded UI toolkit model doesn't mean that we necessarily have to stop everything happening in the application in the meantime.
So let's talk a little bit about shadows. So shadows are obviously, and I'm sure by now you figure that out, an important part of material design. Creating shadows on Android is super easy. Like Chet mentioned, all you have to do is set an elevation on the view. And as soon as you have an elevation set on the view, the UI toolkit will capture the outline of a view and cast a shadow based on that outline. So if you're not careful, the outline might not match the visual of your view and will look a little weird. A key thing to understand about the shadows and how they work in Lollipop is that they use an orthographic projection. The whole 3D system in the UI toolkit uses an orthographic projection. So when you set an elevation on the view, you're going to get this beautiful soft shadow, but the view itself will not scale up. It will not look bigger. If we had a real perspective projection, the higher the elevation, the bigger the object will get. So if you want to change to get that 3D effect on the view itself and not just on the shadow, then you need to use the scale X and scale Y properties. You can animate the elevation just like any other property. So there's an example here. You call view.animate the translation Z. You give it the new value, and we will nicely animate to the new elevation. So it will give you a nice animation of the soft shadow. And again, if you wanted to, animate the 3D elevation of the view visually, you would just have to animate scale X and scale Y at the same time. So
I should point out that that we actually had perspective projection to begin with. That we had a full-on, perspective world that we were projecting in, and initially, and as things were raised in elevation, they would actually scale up. They would do the right thing for a perspective world. But it turns out that that's not actually what you want in a lot of cases. It can cause artifacts with text as it sort of crawls and scales up, or it looks blurry at some scales and not at other scales. There's other operations in which, just because things lived at a permanent elevation didn't mean that you wanted them permanently scaled up, or maybe you wanted the effect of them overriding other things but not, being popped up and being larger than them. And it caused a lot of inconsistencies and potential artifacts in the UI. So we made the decision to go to an orthographic projection because frankly that's what makes sense in most UI element situations. The demos that we're taking a look at today where you're actually clicking on images where it's very bitmap or image focused applications, in that case it seemed a little more natural to actually scale things up and to have more of a perspective take on things, which is why we use scale X and scale Y there.
So this is an example of how you use those shadows and the elevation in practice. So this is the code from a custom view. And you can see that we simply animate the scale and the translation, the elevation, based on the actions of the user. So I believe that code was taken from your demo. So as soon as you price an item, it grows bigger, you get a nice bigger shadow, and we can move on to the next activity. So I just wanted to explain a little bit the reasoning behind the shadows and why they are implemented the way they are. So imagine that the light source that's being used on Android is an area light source, so that's that white rectangle over there. And then you have the view itself called an occluder. And the soft shadow is actually made of two distinct sections. So from a different perspective, it's easier to see. We have the umbra. So in the umbra, the area light is not visible at all, completely occluded by the view. And then you have those little soft edges on the sides. It's called the penumbra. It's when the area light source is partially visible. Unfortunately, the pictures you are seeing here were rendered with Blender, and they took something like 10-15 minutes to render on this laptop, so we couldn't implement things in the same way. One last thing to make shadows look more realistic. So this is a naive approach to implementing shadows, but in the real world, you never get completely dark shadows like this. Even if you lock yourself up in a dark room and you close the door, after a few minutes, you're going to start noticing objects and details. And it's because light bounces around. It's a phenomenon called global illumination. And you can see a little bit of an example here. It's hard to tell on the screen over there, but the red color of the view actually reflects onto the ground in the shadow. And the shadow itself is a lot lighter than in the previous example. So the implementation of shadows in Lollipop tries to recreate this effect of global illumination. It's completely faked, but it looks a lot better than if nothing was attempted. Just a little background. Shortly before I left the Android team, I was prototyping the first iteration of those soft shadows. And of course, I tried something stupid, and I tried to ray trace the soft shadows on the GPU on the phone. For those who don't know, ray tracing is extremely expensive. It's basically what Blender does. And I was able to get something that looks actually pretty good. You can see here that was running on a Nexus 4. The result is good enough. And it even had that global illumination approximation, so the shadow is not completely dark. There was just a little problem with that approach. It was running the GPU so hot that after 30 seconds or a minute, the device would reboot. So that was not a good implementation. And obviously, they've done something different for the final release.
We thank you for your input on that project.
Yeah, I tested the other solution first. So the way it works is it calculates a geometry of the view as cast by the area light. So you can project the light through the view, and it will give you a new shape on the ground. That new shape is turned into a bunch of triangles, and that's the shadow. Then there's the global illumination approximation that's done by having a second shadow projected on top. And all those shadows are fully dynamic, so when the objects move or rotate or even scale, the shadow will be recomputed. So it's unlike using PNGs or 9 patches that are completely static. Here you can actually try it pretty easily. When you move objects in a list, if they have a shadow, you'll see the shadow slightly move. It's even more obvious when you rotate them. And to get the soft edges, it's just using interpolation on the GPU. So this is an example of how it works. So that white rectangle here would be your view, and that's the kind of shadow you would get on screen. And really what's being computed by the UI toolkit is something like this. So just a bunch of triangles with gradients, a gradient from dark to completely transparent across multiple triangles to give you this nice soft effect.
So one of the questions that we get a lot on shadows is, isn't that really expensive? Aren't you spending a lot of performance on it? Sort of yes and no. The most expensive part of real-time shadows is the calculation of the mesh, coming up with this fairly complicated set of triangles that represent the mesh. But actually rendering them, you're basically asking the GPU to do something that it is happiest doing in life. We actually don't do enough of this in the UI world, where we tend to send down things that consist of 2 triangles. GPU is very tired of rendering UIs. What it really wants to do is draw something like this. Lots and lots of triangles where it can do something really easy, like interpolate alpha from 0 into some other translucent value at the edge to get that soft shadow effect. So the actual GPU rendering portion of shadows, very cheap. Recalculating shadows, not as cheap. So if you have tons of shadowed objects on the screen, eventually you may see some impact of that, simply because as these views are moving around and we're recalculating meshes, we are using up CPU resources to do that.
So especially when triangles are not textured, as it's the case here, you can draw millions and millions and millions of those every frame, and you can still run at 60 frames per second. So shadows are very useful, they're very easy to use. Just be careful if you try to use 3D rotations on views. So you can rotate a view in 3D by using the rotate X and rotate Y properties. So it's going to apply a perspective projection on the views. But you have to know that the ground has an elevation of 0. So even when you rotate the view itself will never collide with the ground, but the shadow will, because the assumption was made that the shadows will be projected on the ground at elevation 0. So if you want to make 3D rotations work nicely with the shadows, you need to make sure that you have an elevation that's high enough. And the value of the elevation that's high enough will entirely depend on the size of your view. So it's something that you might have to compute yourself. when you create the effect. So play with it, see if you can make it work and what kind of values you need to use.
Also be aware of where the light source and the eye are. If you rotate it high enough, you're going to cause all sorts of weird math and artifacts, but that was already the case with rotate X and rotate Y.
Yeah, with a very big enough, you might end up in a situation, and a rotation angle big enough, you might end up in a case where the view is both above the light and under the ground, and you're going to get results that are completely off.
So one of the reasons to have shadows is to animate them. So the effect that material design wanted on buttons, for example, was for them to react to your touch, not just by having animated ripples and touch feedback, but to actually sort of magnetically attract to the finger. So they're going to pop up a little bit when you press on them. And this is done by using a state list animator that defines not only what that button is going to look like in the new state, what is the pressed color, but also what is the animation that takes us to this state. So we have this new API called State List Animator that allows you to do that. Say, for this following named state, pressed, unpressed, whatever, here are the animations to run to get you there.
So here you can see a little example of an animated state drawable. So if you look, that button on the right, that little fab, I guess, if you look very closely underneath, there's a drop shadow, and when the finger is pressing the button, the shadow grows as the elevation is animated. It's usually a very subtle effect, and here's what the implementation looks like. So in your XML file for your view, so in this case an image button, we just reference a stateless animator, which is another XML file that looks like this. So if you've used stateless drawables before, you might be familiar with that selector and item syntax. And here we just specify two different animators based on for the two different states. So for the press state at the top, we just animate the translation Z, the elevation, to the pressed elevation, so higher up. And in the normal state, so anything that's not pressed, we animate back to 0. You can also load those animators, so they're declared from XML. You can load them pretty easily using an animator inflator. So that's very similar to what you do for other animations.
So one of the new APIs that we came out with in Lollipop was around activity transitions. So the idea that you can have much richer animations between new activities, between activity transitions, or going from one window to another, essentially, than you could before. Window animations on Android traditionally have been animations that are really confined to the overall Windows surface. The window manager doesn't know anything about the contents of the windows. Instead, it can only animate the window surface itself. So that's why you can do simple things like sliding a window up, which is the new window transition on Lollipop, or scaling and fading the windows, which were the standard window transitions from Holo and on in 3.0. But you can't do anything with the items that are actually inside the window. What we wanted for window animations or activity transitions in general in Lollipop was twofold. One, the ability to animate the items in the window themselves. You can animate items out that are going away. You can animate items in that are coming into being in the new activity. And the key part is the ability to animate items that are actually shared between windows. So here you can see we're clicking on one of the views. This pops the card up, and then it says, okay, launch a new activity and share this element. And that kicks off the system that says, okay, well, where is that element going to be in the new activity? And then I'm going to animate its size and position change according to that information that was calculated in the layout in the new activity. So there's defaults for this. If you just opt into activity transitions, we'll do something reasonable, which is basically going to do fading of items that are coming and going and repositioning and resizing of things that are changing position and size. But you can also customize these animations. So you can have an explode animation that tosses things off the screen in a more staggered manner, or you can define your own custom transitions and animations. So you can opt into window content transitions. Actually, I should point out that activity transitions are enabled by default if you're running in the material theme, so you don't actually need to opt into this. You're already opted in just by running in the theme. Window content transitions are something slightly different, which is when you set the content view on your activity, then we will automatically run an animation if that attribute is enabled. So this is slightly different than the activity animations we were talking about. Then you can, if you want to opt into this thing, if you want to actually run an activity, activity transition. You can set different behaviors there, so you can set a specific transition to be run when things are exiting, or you can set a specific transition to run that animates the shared elements between these activities. You can allow overlap behavior, which means do the entering and exiting animations overlap, or do I want one to run before the other one starts? And then you can set up the shared elements, and you basically create a bundle of information that says, here are the elements that I'm sharing from the launching activity. You put them into this bundle, you launch the new activity with that bundle, and then the new activity will run. It'll take a look at the bundle and say, oh, I know what an album cover is. I'm going to enable the following animation based on that. And then the framework takes care of all the details of automatically animating this stuff. So the activity transition stuff builds on the transitions API, which was enabled in KitKat, which is basically, it's building on the animation framework that already exists, but its intent is to simplify animations. Instead of you having to manually construct animations whenever you want to move stuff around, it does a bunch of automatic calculations for you, where when you tell it that you want a transition to run, it says, okay, I'm going to quickly measure where things are right now, and then it's going to allow layout to occur so that everything is put in its new position, and then it'll figure out where things are then, and then it'll rewind the state and say, okay, now play animations to get to the new state. This is using techniques internally that we've talked about in some of the dev by tutorials and articles that we have out there for running animations, where you can add a pre-draw listener in that allows you to run layout and then capture state of the view hierarchy, and then go back and run animations that get you to that follow-on state. So this is the new API that we enabled in KitKat. Hopefully people are using it already. We're building on it in Lollipop to add new transition capabilities, as well as to add the activity transition capabilities, so that now you can not only transition between different states of your activity, but you can actually transition between completely different activities. So you can say, here's where my view hierarchy was before, including these shared elements, and here's where my view hierarchy is in the new activity, including, again, the same shared elements, and then it'll automatically run an animation for you. Excuse me. You could already do this. In fact, there's a dev byte out there called Custom Activity Animations that shows you how to do this technique already. It's not intuitively obvious, which is why we did a video tutorial on it. It's also not highly performant, because the technique is basically to pop up a transparent activity on top of the existing one, and then once you have that activity in there, you can pass information over in a custom bundle, and you can extract that information, then you can run whatever animation you want. But in the meantime, your window on top, even if it looks opaque, it's transparent as far as the system is concerned, which means we're keeping around resources behind it and sort of wasting those system resources. With activity transitions, we're able to say, okay, now the animation is done, make this window opaque, and that problem goes away. And also, we just exposed a lot of API and capabilities to make it easier for you to simply opt into this capability, as opposed to you trying to figure out how transparent windows work and sort of manually creating these animations.
So something interesting that is not obvious to do, but it's actually pretty easy to implement, is how you can synchronize regular animations with activity transitions. So if you look closely at this example here, when we press the photo and we transition into the detail activity, because of the transition, the photo will be drawn on top of everything else by the system. But we have those two little icons, the little star and the little map indicator that we want to put on top of the photo. And basically what we want to do is make them fade in after the activity transition is over, because otherwise they would just pop into view and it would be a little jarring. So there's a very easy way to orchestrate all those animations together. So when you grab your window in the onCreate method, you can get the enter transition. So the enter transition is what's played when you when you enter into an activity. And you can add a transition listener, and we can just wait for the end of the transition, and when we reach the end of the transition, then we can just run our own animations. So here we just run a simple alpha animation using a view property animator on a couple of views. It's a little more complicated when you exit the activity. You want to do the opposite thing. You want to first fade out those two buttons and then play the transition. So here we intercept the on-back press method, and we don't call super. That means we're not going to call finish on the activity. We're first going to run our 2 animations and put a listener to listen for the end of one of those 2 animations, and only after those animations are ended are we calling finish after transition. And you need to call finish after transition and finish, otherwise you're not going to get the nice animation. And finish after transition doesn't mean that you want to call finish after the transition is done. It means that you want to run the transition and then the activity will be finished after. It's a little confusing.
Reverse Polish notation for methods.
Pretty much. Something else, let's go back to the video. Something else that's subtle in that video, let's see. So the images are darkened in the list view, but as you can see that when we transition into the activity, we go from that darkened state to the normal state of the picture, so they get brighter and more saturated. So what we have in the list view is a simple color filter with a tint to darken the image, and we want to animate that tint. It was pretty hard to do on previous versions of Android, and actually it was still pretty hard to do in the I/O preview release of Lollipop, and now it's very simple. So you just grab your image view and you can just run a property animator on a property called tint on the drawable that's inside your image view. Tint is just a color, so you here animate from 0, which is completely translucent, to the color tint that I want. Speaking of colors, you can now define a palette in your theme. So by default, material design comes from its own palette, but it's highly recommended you override that palette. It's great for branding your application. You can also use a utility in the support library called palette to extract color information from existing images or bitmaps. So the way this works is that in material design, all the assets by default are in grayscale. And the colors you define in the themes are just used to tint those assets using existing APIs that we have on Android. So we have color filters and various ways of tinting assets. So it was possible to do on previous versions of Android, but you didn't have a good way to grab all the drawables that are inside your window. Some of them, the ones you create yourself, you can easily get access to them and add a color filter on them. But for all the drawables that are created, in the menu bar, in the action bar, in pop-up menus, that was pretty hard. And also, it's going to save you a lot of space in your APK and a lot of space in memory. That means you don't have to bake the colors anymore into your assets. You don't have to use one of those online tools that will generate for you all the assets in different colors at different densities. It will also save memory for the system overall, because we'll be able to share all those bitmaps between all the applications, since they will all be using the exact same bitmaps. So this is an example of theme colors, and you can see that, so in this application that shows a beautiful pink, and you can see that I was able to override the status bar color and the navigation bar color. You don't have to, it really depends on the kind of application you're writing and what your designers want to do. This is how you do it. So I just created a custom theme called base app theme. It inherits from the standard light material theme. And all I did was specify 5 colors. So I have the color primary dark, color background, color accent, and color control highlight. So this is just a pinkish/purplish palette that suits my application. The next 2 attributes, navigation bar color and status bar color, are pretty self-explanatory. They're used to control the color of the status bar and the nav bar. Here I just have a reference to the attributes that are specified just above. So use this question mark and the Android namespace. Again, you don't have to do it this way. It's really up to you what you want to do. And I've also used a reference for the window background. It's always a good reminder. I often have to go look at the source code of Android to remember how to use references. I don't use them nearly enough. This is just a bunch of screenshots from the demo application that show you what you can do when you use this new palette utility from the support library. You can see in every one of them the background of the window, the color of the title text, and the color of the paragraph of text are lifted from the image.
We should point out that theming colors is different than setting them dynamically. So on the previous slide, the colors that we abstracted from the bitmap, we then set dynamically on the background with probably set tint on the drawables.
We're going to take a look at how to do this.
So we'll see that. So the theming is, these are the colors that you want in your activity overall. That's sort of what it starts with. But then if you want to actually set stuff dynamically, you use it through set tint.
So the palette API is part of the version 7 of the Android support library. You give it an image and it will generate a palette of colors. So you're gonna you can specify how many colors you want back. By default, it's gonna give you 16 colors, and 6 of them will have a name. And we're gonna take a look at an example to understand what those names are and how they match to your image. Just be careful when you use the named colors. The return value might be null, so you have to check for that. Because if you supply a bitmap that's a solid color, then the palette API won't be able to extract those 6 colors from it. So this is the example lifted from those are the colors generated by the palette API coming from this bitmap on the left. So we have 6 named colors: dark muted, dark vibrant, muted, vibrant, light muted, and light vibrant. And you can see the full palette that was generated from this image on the right. I took this example because, like I mentioned, by default you're going to get 16 colors, but it's the maximum numbers of colors you can get. In this particular case, I only got back 14 colors from the API. So you'll have to make sure that your code, make sure to test your code against, a fairly large sample of images, or at least try to use it against, a black and white image, a solid color image, and some random photos to make sure that you don't crash when using a color. It can be, using this API, it can be a little difficult at first to figure out like which one of those named colors you want to use in which place. But usually you'll want to go for colors that that have high contrast between themselves. So dark muted for a background, then you can use dark muted for the background, and you can use the light muted as the foreground color, and you're going to have a fairly good match. So this is how the API works. You just call palette.generate, and you pass a photo. There's an async version of this API called generate async, and you can specify a callback. It will work in the background, and then and here I just call apply palette. It's a function in my code. So this is the kind of code that you have to write in your application if you want to colorize the UI based on the palette. It's a little more difficult than using a standard XML theme. So for instance, to change the window background, you have to call getWindow.setBackgroundDrawable, and then apply the color that's coming from the palette. When you call one of those methods on palette, so for instance, getDarkMuted_color, you don't get an object that the Android graphics API can understand, because for Android, a color is always an int. So you have to call getRGB on the color object from the palette. And again, like here, it goes against what I told you a couple of slides ago. I should be checking for null before using any one of those colors. I know, I'm a terrible programmer. This is another example from the demo you saw earlier. So the 2 icons on top of the images use colored ripples. And those colors are also coming from the images. So it's pretty easy to create a ripple drawable from XML, but you're going to be limited to a single color that's specified in your XML file. So I just wanted to show you how you can customize the color of the ripple in code so you can have a more dynamic palette in your application. So this is what the XML file looks like. And you can see here that I've set the color to color accent, and we're stuck with that. So the way to dynamically change the color is to get the ripple drawable from your view. So you call get background on your view, and you get back drawable that you need to cast to a ripple drawable. Then I call get drawable 0. So that gives me a ripple drawable is a layer drawable, so it can contain several drawables. In my particular case, and this is usually the example for all ripple drawables, we have a single item. It's a shape, an oval shape. And shapes, for some weird reason, please don't ask me, map to a class called gradient drawable.
So not shape drawable, gradient drawable.
Because there's also a shape drawable, but it's something else. So you call get drawable 0 to get the first drawable within the layer drawable. You cast it to a gradient drawable, and then you can set color. You can call set color on it to get the color you want. Of course, calling set color would be too simple on the ripple itself, on the ripple drawable, because it expects a state list. So you use color state list.value of, and you pass a single color. And if you want to have different colors based on the press state, on the focus state, then you could build your own state list. But it's pretty difficult to do from code.
So let's talk about circular reveals. So the idea of taking the user from one state of their application to another by revealing that view over time. So sort of having this expanded view where we glimpse into the view as it's expanding, and then you can also have the opposite where it contracts. So you could do this prior to L, and you saw it in such applications as, I think, the Search app, or Now?
Google Now.
I think when you clicked on the search bar in Google Now, then you would sort of see the circular reveal to show the search results or the card results or something. So you could do that previous to L by using a bitmap shader. Not terribly performant. I believe they enabled it for Nexus 5 because it ran reasonably well there, but it wasn't on a lot of other devices because it simply wasn't fast enough to keep up. So we've made that, we took a different approach and added APIs that make that a little bit more performant and general purpose. It's still intended to be a transient action. You wouldn't want to actually shape a view using the techniques that we're using down there. So it's still just an animation that's supposed to reveal it over time and then be done. You wouldn't want to actually have that code running every time you're displaying your view. So in L, you use this create circular reveal in the view animation utils class. So you can see this, we have the expanding reveal and then the contracting reveal when you touch the button again. So the way it works is by using, prior to L, we're using a stencil buffer. Roman can talk more about that.
Yeah, so the stencil buffer approach was if you use on the Canvas API, you can clip using a path or a region. So that's how you could clip to a circle, for instance, to the circular reveal. And I was using the GPU stencil buffer. It's a pretty slow approach because of the implementation of drawing path into the stencil buffer in the OpenGL pipeline. It used also more memory because we had to allocate that stencil buffer. And the stencil buffer doesn't let us do anti-alias clipping, which the new version in L can do. So the new version in L uses shader-based clipping. It's simply whenever the system needs to draw something, it's going to compute the distance of that pixel from the center of the reveal circle, and then we will just modulate the alpha value of that pixel based on that distance. So it's really fast, doesn't use more memory, works with everything, completely dynamic, so the content can change inside the clip itself, inside the reveal itself. So this is what the code looks like when you want to create a reveal animation in your application. It's highlighted in bold, so you call view animation utils that create circular reveal. That gives you an animator, and then you just call start on it. And you get a few parameters. You can specify the view, the position of the start position of the reveal in the view coordinates. So here that's the variables called Cx and Cy. And then you specify the start value of the start radius of the circle and the end radius of the circle. And it's going to animate between those two values. And that code came from our demos. And what we do is when we receive a touch event, we just look at the X and Y position of the touch event within the view. Then we just compute the center of the view. Do you want to show?
Yeah, I wanted to show. Can we run the videos of that demo again? Sure. One of the things that we did not have in the preview release, but which is out in Lollipop, is animated vector drawables and vector drawables themselves. So this is the idea of using vectors to describe your icon assets instead of the traditional bitmaps or PNG files. So much more potentially memory efficient. You don't have to create all these PNGs for all these different form factors and resolutions. Instead, you can supply this vector, which then scales to all resolutions. So I wanted to show a very simple example of that here. So we have this sort of silly eye animating into an X over time, and then we also have a circular reveal, and I wanted to show a little bit of the code involved there. So we'll pop into the IDE. There's a bunch of code here. You don't have to worry about most of it. I'll just walk through really quickly. So this is very similar to what Roman was just showing. This is actually doing the circular reveal of that orange. Basically, we go from the dot to the full orange background behind the text description. So this just animates that circular reveal. It just gives it the center of the expanding circle, and then the starting radius of 0, and then the full radius of twice the width of the container, and then it just animates that over time. And then we get an animated vector drawable, so this refers to a resource that I'll show you in a second, and we set that as the background on this view. So this is what's going to be used as the drawable. It's also going to be used as the animation to change the state of that drawable over time, and then we start the animation. That runs the animation on the animated vector drawable. Fairly straightforward. Then the details are in info icon animation. Info icon animation here. So animated vector drawable is really a reference to two other resources. One is the vector drawable itself that defines the geometry and the attributes associated with it for the vector. So here we're referring to the drawable called I, and then we're also referring to an animation on that. So this animation, animated vector drawable basically refers to geometry and animation information. So if we take a look at the eye drawable, that would be here. We can see fairly straightforward, a little too much information there that you really shouldn't worry about. The path data, this just uses SVG type format to describe basically moves, lines, and curves for the vector information. Then it defines some other simple attributes like the fill color and the stroke width and the stroke color. And if we go back here to the previous file.
You should zoom on the...
Oh, yeah. Whoa. Whoa. And then we can go take a look at the actual animation that animates between states of the drawable. So we go take a look at the I to X. And this defines the animation. So we have a set, which is kind of irrelevant here because we only have one child in here. We have an object animator that operates on the path data, excuse me, element inside that geometry, and it's going to morph from this representation of the path is the starting point, and this representation of the path is the ending point. The important thing to note is it's simply doing an interpolation between numbers. It's basically using the same approach that SVG does for animations. It's not doing anything complicated. It's not creating new geometry along the fly. It's just saying, given the structure of this path, which must match to the structure of this other path at another point in time, it can interpolate the numbers in between those two representations. And it runs the animation, you give it a duration, you can give it interpolators. This is a standard object animator, so all the facilities of animators are available to you if you want them. Runs the animation, and then you have the different representations. So in that particular demo, I was basically animating between an I representation and an X representation of the icon, and at the same time I was running a circular reveal on the container below that to sort of reveal the full-on orange background for the text description.
And just to be clear, the from value and the to value must have the exact same representation. That means you need the exact same number of points, so the same number of commands. A move must map to a move, a line must map to a line, and a curve must map to a curve. So it wouldn't be easy, for instance, to turn a circle into a star. I mean, there's very little reasons to do that anyway, but just be aware that if you're getting weird results or if the system throws an exception and doesn't want to play the morph animation, it's probably because you have two representations that don't match very well.
You want to talk about path tracing?
Yeah, so this is not related to L directly, but I think it's a cool little visual effect, so I wanted to talk about it. And it's, I find it interesting because it actually works all the way from API level 1, so Android 1.0 to not L preview to API level 21. There we go. I previously presented this effect using an API called Path Effect, and I realized today there's a better way of doing it. It's called using something called path measure.getSegment. And I'll show you this new solution. So this is what it looks like. That's the demo you saw earlier, and I'd written another demo before where you can see a map of the United States being traced, like text appearing with that effect. So if you want to create an in L, if you have the new Play Movies application, when you touch a movie that's being played and you scrub, you'll see little arrows that appear on screen, and they use a similar effect. So if you want to do this in your application, it's pretty easy. You have a path. It can be whatever you want. So you make a path. You can get it from an SVG file. It's up to you. Then you create a render path. The render path is just a container for the segmented version of the path. Then you call a path measure object. So the path measure object is mostly used to know the length of a path. So that's what we do here. It's the length in pixels, really, if you want, of the path. Then we can call getSegment. So getSegment, we tell path measure the segment of the path that we want. So in this case, we want to start from the beginning of the path, so pixel of this at distance 0, all the way to a certain fraction of the length of the path. And then you give it the render path. So what getSegment is going to do is analyze the original path figure out what parts of the path, what commands, what lines and curves to keep, and copy them into the render path. Then if you want to work around a small bug in Android 4.4 and earlier, you need to just do a no-up command, so R-line2. It's not going to do anything. It's not going to create problems on Lollipop. You just need to do that. Then when you're done, you can call draw path. So once you know how to do this, all you have to do is animate that length. So you multiply it by a fraction, a number between 0 and 1. So for instance, you can create a value animator. We're going to animate from 1 to 0. And then on every frame of the animation, we're going to call path measure.getSegment again. And we're going to multiply the length of the path by that value between 0 and 1. And that's it. You're going to have your nice animation. So very easy to implement. And L actually gives you this capability through public APIs on VectorDrawable. So it has trim start, trim end, and trim offset. And those map to the values that are passed to path measure.getSegments. So if you have a vector drawable and you want to display only part of the drawable, you can use those attributes, and you can also animate those attributes.
Yeah, I should have pointed that out earlier. I was showing how to morph a path between different representations of the geometry, but you can also animate any of the other properties that are exposed in VectorDrawable. So these are some of them there. You can also animate the stroke width and the stroke color and the fill color.
And that's all we have. We have about 10 minutes left for questions.
And it's really hard to see hands. Yes?
So with card view, some of the examples have like a full blade image at the top. And if you've got rounded corners, do you get that like clipping of the image for free with card view, or do you have to still do that yourself?
So the question is, if you're having full bleed images in your card view, what happens to the image at the edges of the card? I believe
on previous version of Android,
on previous versions. On Lollipop, it would automatically, anything that goes to the edges of the card would be clipped because the view is actually being clipped. On prior versions, we couldn't actually do that. So we're using, traditional Android workarounds for that, where we're just drawing the bitmap with rounded corners instead. And at that point, yeah, I think you want to back your full bleed images off to not go all the way to the corners. I think, is there padding on the contents of the view as well?
It's up to you.
Yeah. So I would work with a combination of padding and just make sure that you don't go all the way to the edges if you're running on prior versions. Yes? I'm sorry? The light source for the shadows is, I believe, centered over the display screen, but sort of toward the top of it. So if you can imagine, if this is the device here, the light source is sort of there, right?
Can you move it? No, you cannot move it.
No. No, not movable.
Is it possible to animate out the action bar without using the toolbar? Like, on this to the Google Play, you'll get into the game section when you scrolling up, and then you animate out the action bar, but then the sliding tabs are floating on top of the screen.
So the question is it possible to animate out the action bar without using two bars?
No, the toolbar.
Oh, the toolbar.
Right. So with toolbar, you have a lot more customization capabilities anyway. But the question was, could we do it with the standard action bar?
I'm sure there are ways. I haven't tried it myself, so I don't know. But it sounds possible. I mean, the action bar is just a view. The only problem I can see is that if you have a translucent status bar, then just moving the action bar won't be enough, so you might want to clip it or something like that. I would have to look at it.
Is there any influence in battery life on those animations?
So the question was, what's the impact on battery life? So yeah, if we're doing more stuff, then that stuff costs something in terms of power. So similarly to what I was saying before, like the cost of shadows realistically is just the cost to recreate them. So if you're moving around a lot of shadowed views, we're going to end up spending CPU resources to recalculate what the new meshes are for those shadows, and that will certainly cost battery life. Not anything significant, and most of these should be transient effects anyway. So a lot of the new capabilities, a lot of the new rendering capabilities were really around animations, which by definition are transient and temporary. So not that the shadows are temporary, because that card is going to be casting a shadow full time, but the act of moving the card on the screen is by definition temporary, right? It's the user moving the notification panel up and down or whatever.
And to this, I would add that the extra CPU and GPU required for those effects is negligible compared to what the screen, just having the screen on, that's going to be the #1 battery killer. And then if you have the radios on, like because you're doing networking operation, that's going to far outweigh the cost of those operations. So yeah, there's an impact, but compared to, like I said, just turning the screen on, it's not going to matter really.
So we would encourage you to keep your screens off at all times.
The animations are
very power
really
efficient.
smooth in that case.
In fact, if you just turn the device off, it can retain battery power for a long, long time. Yep. Yeah.
So with the elevation, is it possible to get shadows projected through an image's upper layer?
The question was, is it possible with elevation to get shadows projected through an image's outer layer?
Alpha layer.
Alpha layer.
No,
Yeah.
not at the moment, because the way the geometry is computed, so you basically take the light source, and for each corner of the light source, you cast a ray through every point of the outline. So with an arbitrary outline, an alpha mask for a bitmap, that would mean through every pixel in the image, and that would be really expensive. Real-time shadows, real-time soft shadows in particular, is a very interesting field where there's a lot of work being done, and nobody has solved it in a very satisfying way. I actually have at home, I have a book that's just about shadows. It's like 300 pages, and every single solution sucks in one way or another. And you can see it in games, where they use a lot of GPU, and there's always a trade-off somewhere. And for Android, the biggest priority was quality. In games, it's okay if your shadow is pixelated or not perfect or doesn't match exactly, the contact point on the ground. But in a 2D UI, we can't do that. So hopefully in the future, and that's why I started with ray tracing the shadows, because then you get a perfect shadow. But rebooting the device is not a cool thing to do. So maybe someday, hopefully.
Yeah. Are all SVG commands supported? No. So we didn't go with the SVG format because we were specifically limiting it to a subset of capabilities of SVG. SVG does a lot.
Yeah, but in the path data,
The path data itself, it should carry over one-to-one. But we're just using that as like a convenient way of specifying exactly the same kind of stuff. I want to move, I want to draw a line, I want to draw a curve. But a lot of the other attributes in SVG, not necessarily, and the types of geometry that you can have in SVG are inherently more robust than the kinds that we're going to handle. We're going to expect your paths to be closed and non-intersecting, non-self-intersecting. So I would say not all SVG content would carry over, but reasonable content that you want for icons should. Yeah.
Can we cast shadows for bottom with
Can we cast shadows from non-rectangular objects? You can certainly set an outline shape and tell us what shape to cast.
Yeah, no, again, that wouldn't work. Right now, the outlines are limited to rectangles, rounded rects, and circles, which are basically all rounded rects anyway, just with a different radius for the corners. And again, that goes back to a previous question, it's because it would be very, very expensive to do it with arbitrary shapes. Again, so I'm sure someday there will be a better solution. But.
Yeah, there were a lot of simplifying assumptions that we had to make to actually hit 60 frames a second. The shapes on shadows and the shapes on clipped views.
Well, and also it only works, the shadow caster has to be concave. Convex. Sorry, I always get them confused. It has to be convex. So you couldn't cast a shadow through a donut shape, for instance, because that's complicated.
Donuts.
Yeah, I know.
I guess that's it. Thank you.
Thank you.